These are the second part of the notes dealing with the focus and the directrix. In this second part, we explore a general form for the equation of that parabola. And that form is, we saw this already, the x minus h squared, and on the right-hand side, y minus k, where the vertex is h comma k. It turns out, however, that the number that sits in front of the x minus h quantity squared has a relationship that I can find without having to do a lot of additional algebra. So we're going to derive this formula, and then we're going to use it. So the derivation may be something that is difficult for you, or it may be something that you find to be really interesting. Stick with it as much as you can so that you can make some connections here. So the first thing we're going to do is we're going to have generic letters, because that's how we derive stuff, for each of the important pieces of our parabola. Our focus, we're going to call the point C comma D. Our directrix, we're going to say that's the equation y equals p. And our point is still, it's our arbitrary point, so x comma y. So the first thing that I want to do is I want to identify where the vertex is. So you'll remember from previous problems that the vertex is going to have the same x coordinate as the focus. So it's going to be at C. It's going to be somewhere here. And that somewhere turns out to be exactly halfway between the focus and the directrix. So halfway is the average. So that's going to be half of the y coordinates. The average of the y coordinates. So now let's look at the derivation. So for our derivation, we're first going to start off by setting up the equation of distance. So we have the distance between our arbitrary point and our focus. So that's this distance right here. You remember we make that lovely right triangle. I have my change in x and my change in y. There's my change in x. There's my change in y. The second part of my definition says that the distance from the point to the directrix is going to be the same. These are, whoops, sorry. There, my point to my directrix, should have drawn my triangle above it, is going to be the same. So this distance and this distance are going to be the same. And so we write that as the change in y only, but quantity squared in order to have it be distances squared. Now, just like in the concrete problem we did in the last notes, I am going to multiply out my y parts, but not touch my x minus c quantity squared. That's already done. It's completed. Completed the square is done. Don't need to touch it. So I expand it out, and then I simplify. My y squareds cancel. I had to add 2dy on both sides, and I had to subtract d squared on both sides. Now here comes the part that, mathematicians see some patterns when they're doing this type of thing, and we wouldn't expect you to be able to derive this, but the derivation is really impressive. And so it's kind of a little bit like you see some tricks and you try them out, and oh look, things start to fall out and they're really nice. So the first thing I'm going to do is I recognize that this is a difference of squares. And then I look over here and I see a d and a minus p. So the first thing I'm going to do is I'm going to isolate the y. So I want my y alone. When I do that, I have a 2 and a d minus p. I then look at this piece and I say, well, in order to have the d in the front, I really need to have the d be the positive. So I factor out a negative sign. So I change my p squared to be negative and my negative d squared to be positive. Next up, I just switch these, just rewrite them so it's d squared minus p squared. So I just want to keep highlighting this y. So now I have a perfect difference of perfect squares, so I can factor that. And now, really, the reason why I did that is because here's a d minus p and here's a d minus p, which means that I can factor a d minus p out. Now, because I want the y here to be y minus or plus something and not have a coefficient in the front, I also need to factor out a 2. When I factor out a 2 from this part, I simply am left with y. However, when I factor out the d minus p, I'm left with d plus p. But when I factor out a 2 here, that's the same as dividing by 2, which is the same as multiplying by 1/2. Okay, my last step is to move this part over to the left-hand side so that I have the form that I was looking for. Now let's do a little bit of checking here. First, I can see the vertex now. It is C, comma, 1/2 d plus p. So that's the same vertex as we got when we looked at the graph. So the graphical representation of the vertex and the algebraic representation are the same. So if I'm looking back at the general form of my equation, I now can recognize that h equals c and k is 1/2 of d plus p. So that gets me all the way to the place where I have what my h and my k are. This is the part that I'm missing. How does the 1 over 4a relate to the 1 over the quantity, 2 times the quantity d minus p? Now I need to go back and look at the definition of what a is. So it turns out that A is going to be the distance from the focus to the vertex. So I'm looking at distance. Let's go back and look at my original picture here. So I'm looking from the vertex to the focus. So that is this distance right here. And I either can recognize that that distance is 1/2 of d minus p, 1/2 of d minus p, or I can do the whole process of the Pythagorean theorem again. So I have here my a squared, my distance is going to be my change in x's squared plus my change in y's squared. If I set up Pythagorean theorem, turns out that I can simplify c minus c. Remember my focus point is c comma d, and my vertex is c comma 1/2 of d plus p. So there's my c minus c. There's my d minus 1/2 of d plus p. But c minus c is 0. 0 squared is 0. That disappears. And then, because I have 2 perfect squares on both sides, I can square root both sides. And now I want to simplify this a little bit. So I distribute my 1/2. I combine like terms. And then I'm going to factor out a 1/2. And then I can get d minus p alone. Let's go back and look at the previous page for a second. In this equation, I have this 2 and a d minus p. D minus p. So now that I have a d minus p, I can go back and I can replace d minus p with 2a, c with h, and the 1/2 d plus p with k. So here's my equation. Let's replace. So I have 1 over 2 d minus p, which we said is 2a. That's what we found up here. X minus h, our c and h are the same, equals y minus our 1/2 times d plus p is the k. And now the only thing I have to do is simplify this last part. 1 over 4a, x minus h squared equals y minus k. And lo and behold, I have now derived this form of the equation of a parabola. 1 over 4a times the quantity x minus h squared equals y minus k, where a is the distance from the focus to the vertex. Okay. If you found this last part of the conversation confusing, do not stress out. I wanted to make sure that you understand that this formula, 1 over 4a x minus h squared equals y minus k, doesn't come out of thin air. We derive them. This exists because of the relationships between the focus and directrix and a point and the vertex. So now we're going to do a concrete example to see how this works out and put this into place. So you remember that, so let's just say I have the focus here and I have my directrix here. You'll remember that the vertex is in between. So in our case, our vertex is going to have the same x value as the focus, so 3, and then it's going to be halfway between the focus and the directrix, so the average of the y values of the focus and the directrix. So that's 1/2 of 9 plus -1, which simplifies to be the point 3, 4. So I can plug that in now. So I now can say that my equation is 1 over 4a x minus 3 squared equals y minus 4. So now I need to find my a, and then I'm done. So remember, we go back and we say, well, a is the distance. So a is this distance. So we say a is the change in y's. So my vertex y is 4, and my focus y is 1. So my change is 4 minus -1, which equals 5. So now I can plug this back in, and I get 1 over 4 times 5 times the quantity x minus 3 squared equals y minus 4. And then I simplify. 1 over 20 times x minus 3 squared equals y minus 4. Now the last thing I want to do here is I really want to make sure that I've gotten my parabola in the right direction. Because depending if I write this as -1 minus 4 or 4 minus -1, it's going to change the sign of this. And so just to be very sure, I'm going to go back and look at where these end up. And so it turns out that the picture I've drawn is actually not that accurate, because it turns out that my directrix is actually above my focus, which means my parabola is facing down. And a downwards parabola has a -a.